In the last couple of videos, we talked about how to multiply vectors, and in one of our earliest videos, we talked about scalar multiplication. So if you have a scalar alpha and you want to multiply it by a vector, you just component by component multiply alpha times x and then alpha times y and alpha times z, and the result was a vector. So that's multiplying a scalar times the vector. So the question became, how can we multiply two vectors together? And the answer, there are two ways to do that, the dot product and the cross product. We saw in the last video, when we do a dot b, use the dot product, that would produce a scalar. In this video, we are going to look at a cross product, a cross b, notated with this bold multiplication sign, produces a vector. So if A is a vector in Rn, let's say R3, and B is a vector also in R3, then A cross B will give you a vector in R3. In this video, these are the main ideas we will be covering about the cross product. First, we will overview determinants or review determinants. So the determinant of a 2x2 matrix, and the idea is this matrix is, two rows, two columns. The indices, the first indice denotes the row, so this is the first row. The second indice denotes the column. This is the first row, first column, first row, second row, first column, and second row, second column. The determinant, which is denoted with these brackets, the straight lines, is just a cross multiplication. So A11 times A22 minus A12 times A21. To get the determinant of a 3x3 matrix, you take this first row, and they are going to be multipliers of these 2x2 matrices. I'll talk about how to get these 2x2 in just a minute. So A11 is your first multiplier, A12 is your second multiplier, and your A13 is your third multiplier. Again, they come from the top row. To get the 2x2 matrix that A11 is multiplied, you delete the first row and the first column. So essentially, because A1, it's the row that A11 is and the column that A11 is, those get deleted, and what's left is the 2x2 matrix you're going to multiply A11 by. To figure out the 2x2 that A12 gets multiplied, well, here's A12. So you delete the first row and the second column because it's A12 is the first row, second column. Again, you delete the row and column that A12 comes from, and what's left is the 2x2 matrix A21, A23, A31, A33 that gets multiplied by your second multiplier. And then last, you have this A13 multiplier, so you get rid of the first row and third column. In other words, you get rid of the row and column that your A13 comes from, and what's left is your 2x2 matrix. And now you know how to get the determinant of the 2x2s, you multiply, and this is how you get the determinant of a 3x3. The cross product of two vectors, if V is V1, V2, V3, and W is W is W1, W2, W3, then the cross product of V cross W is equal to the determinant of the ijk direction vectors with V in the second row and W in the third row. And remember, the cross product of two vectors should give you another vector. So for an example, we have 3, -1, 1 crossed with 1, 2, -1. So I put the ijk vectors, my 3, -1, 1, and my 1, 2, -1. So I have my I, cross out the first row and column, and this is the determinant I get. I have my J, cross out the first row, second column, and this is the 2x2 determinant. And then K, cross out the first and third, and this is the 2x2 determinant I get. When I do all the multiplication out, the final vector I get is -1, 4, and 7. So again, what you get from a cross product of two vectors is again a vector. And that's very important. And the other thing, which we will talk about more, is that this vector is perpendicular to the plane spanned by V and W. The properties of the cross product, so they don't commute. So V cross W is not equal to W cross V, but it is equal to negative W cross V. And this negative, we'll talk about that, well, when we talk about the right-hand rule, it just points the other direction. Then we have the kind of this distribution law and another distribution law with an alpha, with a scalar alpha. Here, the u and the v and w are all vectors. Alpha are scalars. My Greek letters tend to be scalars. My u and v's and w's, those tend to be vectors. Equally as important as this algebraic definition of the cross product here, actually here's the definition, is the geometric interpretation. So first we should note that v cross w is equal to the norm of v times the norm of w times sine of theta, theta being the smaller angle between v and w. The other important thing to know is that v cross w is a vector perpendicular to the plane spanned by v and w, with length norm of v, norm of w, sine of theta. I tried to draw that here. If we have two vectors v and w, they define a plane, which I'm just going to shade in yellow. And the idea is this v cross w vector now is perpendicular to both the v vector and this w vector. So it's perpendicular to this plane. Since there are two choices of direction that are perpendicular, we use the right-hand rule. And by two choices, I mean, well, think about it. If you have a plane, like let's say a sheet of paper, perpendicular, you can think of an arrow pointing up, or let's say your plane is a table. You can have a perpendicular vector pointing up out of the table, but you can also have a vector pointing down into the table, and that will also be perpendicular. That's what I mean by two choices, and I'll show you the right-hand rule when we discuss this in more detail. And if v and w are collinear, then v cross w is 0. Also, v cross w has a geometric interpretation as the area of the parallelogram with adjacent sides vw. So we made a little parallelogram. This v cross w would be the area. Last, we're going to take another look at the equation of the plane with the normal vector n equals abc and containing the point x naught, y naught, z naught. And we talked about this a little bit when we talked about dot product. We're going to look at it another way using cross product. So that's an overview of what we're going to cover in this video. So now we can go through each topic in more detail with more examples. The first thing we need to know about are how to calculate determinants denoted for a matrix, and we're going to be concerned with 2 by 2 and 3 by 3, and they're denoted with these bars. And as I mentioned, the 2 by 2 is just a cross multiplication, and A11, A22 minus A12, A21. For the three-dimensional, the 3 by 3 vectors, the top row becomes coefficients. And the thing about the coefficients, which I forgot to mention in my overview, is they alternate in signs. So the first coefficient is A11, the second one from our top row, again, is A12, and it has a negative. Our A13 is over here as our last coefficient. So our first row is our coefficients. From there, we multiply by 2 matrices. And to get the 2 by 2 matrix, we look at these, the indices on here, and we delete the row and column, and we take the remaining 2 by 2 matrix. So for example, A11, we're going to delete the first row, first column, because A11 comes from the first row, first column. And the remaining matrix, 2 by 2 matrix, is what we multiply A11 by. For the A12 coefficient, because it's in the first row, second column, we delete the first row, second column, and the remaining portions are our 2 by 2 matrix, A21, A23, and A31, A33. Finally, for our A13 coefficient, we're going to delete the first row, last column, and what remains is our 2 by 2 matrix, A21, A22, and A31, A32. Now we can define our cross product. V cross W will be equal to the determinant of ijk with V components as our second row and W components as our third row. For example, if we want to take the cross product of 3, negative 1, 1 with 1, 2, negative 1, we write our direction vectors I, j, and k, and then we have our 3, negative 1, 1, and then our second vector 1, 2, negative 1. And just to clarify, I, j, and k, when I say there are direction vectors, so I is in our vector in the x direction, so it's equal to 1, 0, 0. They're all unit vectors of, so unit length 1, j is in the y direction, so that's 1, 0, 1, 0, and our k unit vector is in the z direction, so that's 0, 0, 1. So in the end, what we're doing is we're multiplying by a direction when we have these I, j, and k's. But anyway, so we start with our I vector here, that's our 1, 1, and then since it's in the first row, first column, the remaining 2 by 2 matrix is going to be minus 1, 1, and 2, minus 1. For the j multiplier, since j is in the second row, second column, first row, second column, we get rid of the first row, second column, and we're left with 3, 1, 1, negative 1. For our last k multiplier, since k is in the first row, third column, we get rid of our first row, third column, and we're left with our matrix 3, minus 1, 1, 2. Now I'm going to have my I times cross multiplying. I have minus 1 times minus 1 minus 1 times 2. Then my minus j cross multiplying, 3 times negative 1 minus 1 times 1. Ooh, this is positive and positive. I'm not sure why I put, but it doesn't matter because there. And then I have my k, 3 times 2 minus negative 1 times 1. So what this gives me is my I, this becomes my 1 minus 2 in my j direction. I'm going to have a minus 3 and a minus 1, and in my k direction, I'm going to have a 6 and a plus 1. So I have so what that gives me is a minus 1 in the I direction, a 4 in the j direction, and a 7 in the k direction, which is just minus 1, 4, 7. And if it helps, although really you should get used to this, the I, j, and k directions, this is minus 1, I is the unit vector in the x direction, plus 4 times j is the unit vector in the y direction, plus 7 times k is the unit vector in the z direction. So you can expand it out this way, and your final answer is minus 1, 4, 7. The other thing is this note here, that the cross product, as you can see in our example, it took two vectors and it produced a third vector. So the result of a cross product is always another vector. If you have a 3, when you take cross products, they're always the same dimension. So if you have something in R3 cross R3, you get a vector in R3. So that's really important because, if you don't know that, if you're not expecting a vector, you really don't even know what space you're in. Quite literally, you don't realize that after this that you're in R3. Quite literally, you don't know what space you're in. And as I mentioned in dot product, it's okay to be lost, except that at some point you're going to want to convince a teacher or a grader that you know your way around. So the last thing you want to do is just be confused what space you're actually in. The other thing we'll look at more is this vector is perpendicular to this plane spanned by your original two vectors. So this is perpendicular to the plane spanned by these two vectors. And again, we'll look at that in just a minute. So some properties of the cross product. The first one, quite important, V cross W points in the opposite direction as W cross V. It has the same length, but points in the opposite direction. These other two, I don't think I use them a lot. Maybe they're good for proofs. So U cross V plus W is equal to U cross V plus U cross W. And alpha, if this alpha is a scalar, V cross W is equal to alpha V plus cross W. Or you can multiply the alpha times W first and then cross it with V. Now we are ready to look at geometric interpretation. I cleared some things out and moved things up so that I would have a little more space. So the first thing is V cross W is equal to the norm of V, norm of W, times sine of theta, where theta is the smaller angle between V and W. So here would be theta. The more important thing to know, or just as important, or super important, I don't know. The main thing to know is V cross W is the vector perpendicular to the plane spanned by V and W. So when we talked about vectors in R3, we said that two vectors will define a plane, right? We showed that alpha V plus beta W will define a plane. So here I have a vector v and a vector w, and they define a plane, which I guess I'll color in yellow. And then the idea is this v cross w vector will be perpendicular both to v and also to w, and in particular, not just v and w, but all the linear combinations or the plane that v and w span. So this bracket here, angle bracket, is to show that it's perpendicular to v. This angle bracket is supposed to be perpendicular to the plane. So think of this as this the endpoint of this bracket ending on the plane spanned by v and w, and this vector here is perpendicular to that plane. Once you have a plane, there are two choices for direction that are perpendicular. So think of a table in a room, and let's assume this table is perfectly horizontal. So you can think of the vector that points upwards, up towards the ceiling, out of the table. That's one direction that's perpendicular. Or you can think of a vector that points straight down into the table and down to the floor. That's another direction. They're in opposite directions, but they're both perpendicular to the table. So since we have a perpendicular plane, since we have a plane and we want to choose a vector perpendicular, we need to choose a direction, right? Because a vector has magnitude and direction. So we're going to use the right-hand rule. If you've taken physics, in particular electricity and magnetism, remember everyone would be doing things with their fingers and looking at their thumb. So it's the same right-hand rule as that. And the idea is if you do B cross C, your fingers should go from B and then curve in the direction towards C. So the first vector is where you start, the second vector is where you end with your fingers, then your thumb will point in the direction of B cross C. And sorry, I should have mentioned, and you have to use your right hand. A couple of other points: if V and W are collinear, if they're on the same line, then they don't define a plane, and V cross W will be equal to 0. And last, V cross W, which is equal to norm of V, norm of W, sine of theta, is the area of the parallelogram with adjacent sides V and W. So that will be this parallelogram. If I have V, something parallel to W, something parallel to V, this is the parallelogram. The area will equal to V cross W. Our last topic is the equation of the plane, which we had looked at when we talked about dot product. We're going to look at it again. And again, the equation of the plane, it's an important equation to remember. So this is a plane that's perpendicular to this vector n. N stands for normal, is equal to A, B, and C. So it's perpendicular to the normal, and it contains the point x naught, y naught, z naught. So this is the equation of the plane. You can see A, B, and C. That comes from your vector normal. X naught, y naught, z naught comes from your point in the plane. So any x, y, z coordinate that satisfy this condition, this equation equaling 0, is a point on the plane. So this is the equation that defines the plane, and it's important that you remember this because it often comes up, and it's good that you're able to read off the vector normal. But even more important, just as I mentioned in the dot product, is you understand the interpretation and how we are going to get this equation using the cross product. Again, because the understanding of how we derive this equation gives you tools for solving other problems that are almost certainly going to come up in homework and on exams. So it's really the method and the thinking that's important, as well as the equation. I kept some notes here for your reference, and we're going to work a couple of examples. So the first one is to find the unit vector perpendicular to both I plus j and j plus k. We are going to start by noting I plus j is equal to 1, 0, 0 plus 0, 1, 0. Remember, this I is the unit vector in the x direction, j is the unit vector in the y direction, so we get 1, 1, 0. J plus k, this is the unit vector in the y direction plus the unit vector in the z direction, so we get 0, 1, 1. Now when we take the cross product of 1, 1, 0 and 0, 1, 1, I'm going to have the determinant of I, j, k, 1, 1, 0, and 0, 1, 1. So that's the I, cross these two out, and you get this determinant here, 1, 0, 1, 1. You have minus j, cross these two out, and you get the determinant 1, 0, 0, 1. And then the k direction, crossing these out, you get the determinant 1, 1, 0, 1. Now I have I times, and then just doing the cross multiplication, 1 minus 0. the j direction and it's a minus sign, I get the 1 minus 0, and the k direction, I get the 1 minus 0. So I have my 1 and the j, because it's the minus, is a minus 1 and k is 1. So 1 minus 1, 1 is perpendicular to both of the vectors, the 1, 1, 0 and the 0, 1, 1, which is the same thing as I plus j and j plus k. Since the problem asked for the unit vector, we need to normalize our vector. So we need to normalize our 1 minus 1, 1. So we need to know the length of 1 minus 1, 1, which is just the square root of 1 squared plus minus 1 squared plus 1 squared, which is square root of 3. So 1 over square root of 3, 1 minus 1, 1 is the unit vector perpendicular to 1, 1, 0 and 0, 1, 1. The next example is to describe all unit vectors orthogonal to negative 5i plus 9j plus 4k and the vector 7i plus 8j plus 9k. I first convert my minus 5i, 9j, 4k to minus 5, 9, minus 4, and then I have my 7, 8, 9 vector here. And I take the cross product. So the cross product, I have my I, j, k direction vectors. I have my minus 5, 9, minus 4, 7, 8, 9. So for my I direction, then I cross these two out, and my two-dimensional vector, my two-dimensional determinant, is 9 minus 4, 8, 9. For my j direction, then I cross out this row, this column, and my 2 by 2 determinant is minus 5, minus 4, 7, 9. Last, for my k column here, k direction, I cross out these two, this row, this column, and I get the determinant 5, 9, and 7, 8. Now, in the I direction, I'm going to have 81 minus negative 32. In the j direction, and there's a minus in front of that, I'm going to get minus 45 minus negative 28. These numbers are really big, which is disturbing. Plus, in the k direction, I'm going to get minus 40 minus 63. So adding such big numbers. I have 113, 17, and 103. So this is one vector that's perpendicular to the 2 points. And I should also note, I could have done the cross product of 7, 8, 9 with minus 5, 9, minus 4. And by one of my properties, that's equal to the negative of this cross product the other way around. This is mine. Well, anyway, so both of these vectors are orthogonal to my two original vectors. But now it asked for, over here, describe all unit vectors. So I need to normalize. So I'm going to look at the length of my 13, 17, 103 vector, which is this huge, ridiculously large number. So if I want to normalize my vectors, it's going to be, and my two vectors are going to be plus or minus the length of my vector, 1 over the length of my vector, which is 1 over square root of 22, 667, times my vector 1, 1, 3, 17, 103. And again, plus and minus, they are both orthogonal. Our next example is the equation of the plane normal to the vector n equals abc and containing the point x naught, y naught, z naught. And the equation is given here. We looked at this problem and actually developed this equation in our last video with dot product. So in this video, we're going to review what we did with the dot product to come up with this equation, and then we're going to extend, make this problem harder. Again, this is the reason why it was important to understand how the dot product played in, so we can kind of do variations on that. But let's start with this first, just developing the equation, which is a review of the dot product. And this is what we did in the last video. So we considered a representative point on the plane. So that would be the point XYZ. I'm going to just draw it here, XYZ. Then the line joining the points XYZ and x naught, y naught, z naught must be on the plane since both points are on the plane. And here I've drawn my line between, it's kind of wavy, but just pretend like it's straight. X naught, y naught, z naught, and x, y, z. Now, again, this line must be on the plane. And also, just to review, the equation of a line from point A to point B, from A to B, so there is a direction associated with this, from A to B is B minus A. So here I have the equation of the line from point x naught, y naught, z naught to x, y, z. And this equation is this line segment, or it's a vector. It defines a vector in the plane. And since the plane is perpendicular to the normal, then this vector, which is x minus x naught, y minus y naught, and z minus z naught, dot our normal vector ABC is equal to 0. And this is from our super important corollary from our last video. That is, if the dot product of two non-zero vectors is 0, then they are orthogonal. So what this gives us, the dot, we have A times our x minus x naught plus B times our y minus y naught, and C times z minus z naught. So this is how we developed the equation of the plane. So any point x, y, z, any x, y, z coordinate that satisfies this equation is on the plane that's normal to n, which is ABC, containing the point x naught, y naught, z naught. And the other thing we talked about in our last video, it would be a mistake to think you can dot this x naught, y naught, z naught and dot it with our normal and say it is equal to 0, because x naught, y naught, z naught is not a vector in the plane, it is a point in the plane. And just to remind you, x naught, y naught, z naught represents a vector, but this x naught, y naught, z naught is the point where the head of the vector ends, where it ends, right? It starts at 0, 0. And it is true, we can move this vector around, as we saw when we talked about vectors in R3. That was one of our first videos. We can move it around. But when we represent it with the coordinates x naught, y naught, z naught, we're starting at the origin and we're ending at x naught, y naught, z naught. So this vector is not necessarily in the plane. It's just the point x naught, y naught, z naught that is in the plane. So what we had to do to make a vector in the plane is we took a random point or a representative point on the plane and then drew a line between our x naught, y naught, z naught and x, y, z. And that then is perpendicular to our normal. A quick example on using this equation or these ideas: determine the equation of the plane perpendicular to 1, 1, 1 and containing the point 1, 0, 0. Certainly, you can just plug these points into this equation and you'll get the same answer that I will. But if you don't like memorizing these equations, which by the way, it's kind of handy, because if you're ever asked to look for a normal of something perpendicular to this equation, and they may not even say it's a plane, it's super nice to recognize it as a plane and just pick off A, B, and C as your normal. But anyway, if you don't want to memorize it, this is how I would approach this problem. Also, it gets you thinking about what you're doing. Take a representative point, x, y, z. Then you make your line between x, y, z. So you're going to subtract x, y, z minus your 1, 1, 1, 0, 0. That's the point on the plane. So you're creating this line with this, the subtraction of x, y, z minus 1, 0, 0. And then when you dot it with your vector normal, you should get 0. Once you have that set up, it's super easy to go from there. X, y, z minus 1, 0, 0 is x minus 1, y, and then z. And then I'm dotting it with 1, 1, 1, so I have x minus 1 plus y plus z equals 0, which gives me x plus y plus z is equal to 1. So this is the equation of the plane. And of course, you can do this by formula. N is equal to ABC, which in this case is equal to 1, 1, 1. X naught, y naught, z naught is equal to 1, 0, 0. Plug it into the formula, you get the same equation. But where's the fun in just plugging into the formula when you can think about what you're doing? This next example is to find the equation of the plane containing the points 1, 1, 1, 2, 0, 0, and 1, 1, 0. The picture we have now are 3 points on a plane. So actually this picture may not be exactly these 3 points given in the problem, but just conceptually, we are given 3 points on a plane. As far as my formula is concerned here, I don't need 3 points. What I need is a vector normal and then a point on the plane. Well, I can use any one of these 3 as a point on the plane, but I need to create a vector normal. And I can create a vector normal if I have 2 vectors that lie on the plane. And since I have 3 points, I can define 2 vectors. So let's just say one point. Let's say the endpoint of my 2 vectors, I'm going to choose the 2, 0, 0 to be my endpoint. my 1, 1, 1 to be this point here, and 1, 1, 0 to be this point here. So now I can do my 1, 1, 1 minus 2, 0, 0, and that will give me this line segment, this vector in the plane, as well as now I have 1, 1, 0 minus 2, 0, 0, another vector in the plane. And just to be kind of give a little more indication, this negative 1, 1, 1 is the line from 2, 0, 0 to 1, 1, 1. So I've underlined this in blue, and I've made this the blue line. And this green, negative 1, 1, 0, is the line from 2, 0, 0 to 1, 1, 0. So it's this green line here. I also want to mention when we talked about subtracting two vectors way back in the video about vectors in R3, that was one of our first videos, there is a direction associated with a vector minus a vector. That is, this is the vector that it's coming from, and it's going to this vector. So here the direction is coming from 2, 0, 0 out to 1, 1, 1, and this is going from 2, 0, 0 out to 1, 1, 0. So I have the arrows to indicate direction, and it's important that when you do this subtraction and you choose these two vectors, whatever point you want, you need to anchor these two vectors to the same endpoint. So this vector starts at 2, 0, 0. This vector also starts at 2, 0, 0. They need to start relative at the same kind of endpoint or origin. Because of that, it would be wrong to do the 1, 1, 0 minus 2, 0, 0, which is this vector here in blue, but I also kind of dotted it in red, and then choose 1, 1, 1 minus 1, 1, 0, because this would start from 1, 1, 0 and go here. So they'd end up at the same point, which wouldn't give you correct results. And again, the idea is you need to start at the same point. You need to have kind of a same point of origin. Now that I have two lines on the plane, I can now go and figure out the vector normal to the plane by doing the cross product. So I'm going to have the vector normal as the cross product of negative 1, 1 and negative 1, 1, 0. Again, I have two vectors on the plane. The normal now is going to be the vector that is the cross product of the two. So I'll do the cross product, which I'll let you do the calculations and verify that it's negative 1, negative 1, 0. This is now my vector normal. I can choose any one of these 3 points as my point on the plane, and I'm going to choose 2, 0, 0. So now I have a vector normal, I have a point on the plane, so my representative point x, y, z minus this point, so x minus 2, y minus 0, z minus 0 dotted with my normal, now gives me a final answer of x plus y equals 2. This next example is to determine the distance from the plane 12x plus 13y plus 5z plus 2 equals 0 to the point 1, 1, negative 5. So I'm going to start by calculating a normal, and the reason is if I have some point out wherever it is up above this plane, or maybe it's below, but let's just say for now, because it's symmetric if it's below, if it's above the plane, I want to look at the perpendicular distance between my plane and the point, right? Because the distance is the shortest distance. You don't want some slanted line from here out to the thing. You want a perpendicular difference. So I will need to know the normal of my plane. And this is exactly where understanding this formula, or having it memorized, you can read off the vector normal, which is 12, 13, and 5. And then I'm going to normalize it just by dividing out the length of the vector so that I have a unit vector in the direction normal to the plane. I have augmented my drawing now. Remember, the plane is infinite, extends infinitely, and I have this point 1, 1, negative 5, which is not on the plane. And you can verify that. You can plug in 1 for x, 1 for y, negative 5 for z, add 2, and you're not going to get 0. So this point is somewhere hovering above the plane. And the idea is that now to calculate my distance, I'm going to look just perpendicularly down, just a straight line down to the plane, and where the point where that intersects, I'm going to call that point x1, y1, z1, x1, y1, z1, and I want the distance between 1, 1, 5 and x1, y1, z1. And the other important thing to note is x1, y1, z1 is on the vector normal. It's perpendicular. I mean, I could calculate the distance from this point to some other point that's not perpendicular. There's an infinite number of distances, right? Because the plane is full of infinite points. The point is, no pun intended, is I want the shortest distance from this point to the plane, and that'll be along the perpendicular. So I've designated this point x1, y1, z1. That's the distance I'm looking for between 1, 1, negative 5, and x1, y1, z1. But I really don't know anything about x1, y1, z1. I just said I'm going to call it x1, y1, z1. But I have no numbers to work with. So I'm going to look at this other point, x naught, y naught, z naught, which is a point on the plane. And, actually, my example doesn't give me a point on the plane, so it sort of looks kind of bad. It kind of looks like I don't have enough information, except that then I realize, wait, I can figure out a point on the plane because I have the equation of the plane. So if I plug in 0 for x, 0 for y, then z would have to equal to negative 2/5 to satisfy this equation. So I can find a point on the plane, 0, 0, negative 2, 5. So now I can calculate this vector from x naught, y naught, z naught, or this 0, 0, negative 2, 5, to 1, 1, negative 5. This is a plane with an infinite number of points, so there are other points you could have used. You certainly could have tried plugging in to the equation something like x equals 13, y equals 25, z equals 37 or something. But or no, you would have solved for z, sorry. X equals 37, y equals 102. But why would you do that? You would be inflicting all these big numbers to multiply and add. So I would recommend doing as many zeros as possible. I would have plugged in 0, 0, 0, except that wouldn't have satisfied the equation of the plane, because my equation I would have been left with is 2 equals 0. So 0, 0, 0, you only get to plug in two numbers. So I plugged in two zeros, solved for the third. But again, there are an infinite number of points that would satisfy this equation. This is just the one I picked. Now that I have this green vector, I want the length from 1, 1, negative 5 to x1, y1, z1. And what I'm going to use are the projections that we talked about with the dot product in our last video. So this length of this vector is the projection of v, this green vector now, I'm going to call it v, onto our normal vector. We want the shadow of this onto the normal vector. Or we can say we want the component of this vector that goes into making n. So from our video about dot products where we talked about projection, the projection of v onto n is going to be v dot n over n dot n. And fortunately, because we normalized, it seemed like an extra step, but it's easy algebra. Our length of n is equal to 1, so this is just going to equal to v dot n. So finally, my distance is just going to be v dot n, and v is 1, 1, negative 5 and 2/5 dot, my normal is 12, 13, 5 over 18.4. So my final answer will be 0.1087. To review what we have covered with the cross product, first, we learned how to calculate determinants of 2 by 2 matrices and 3 by 3. For the 2 by 2, it's just a simple cross product. A11 times A22 minus A12 times A21. For the 3 by 3, we take the top row as coefficients to these 2 by 2 matrices, and the 2 by 2 matrices are gotten by eliminating the this ith row and the jth column. For A11, we eliminate the first row and first column, and we're left with this 2 by 2 matrix, A22, A23, A32, A33. For A12, and there's a minus sign, I'm sorry, the coefficients alternate in sign. So the A12, we eliminate the first row, second column. So we're left with A21, A23, and A31, A33. And last, we have A13, and then the 2 by 2, we eliminate the first row, third column, and we get this 2 by 2 here. And then we defined the cross product between two vectors, v cross w, as the determinant of ijk with v and w. And we did this example here to calculate it out. And one of the important things we have to know is that the cross product will take two vectors and it'll produce a vector. Here, if we have two three-dimensional vectors, our answer is a three-dimensional vector. We have these properties of cross products. Probably the most important one is V cross W. This does not commute. It is not equal to W cross V, but it is equal to negative W cross V. So it's the same vector in the opposite direction. There's a geometric interpretation for the cross product. So V cross W is equal to the norm of V, norm of W times sine of theta, norm being the length of. And V cross W, more importantly, is the vector perpendicular to both V and W. And it's perpendicular to the plane spanned by P, V, and W. And this is what this illustration was here. If you have a vector V, a vector W, these two vectors will define a plane. V cross W then is perpendicular to the plane defined by V and W. And since there are two choices of direction that are perpendicular, we use the right-hand rule to determine the correct orientation. And if V and W are collinear, if they line a line, then they won't define a plane, and V cross W is equal to 0. And last, V cross W is the area of the parallelogram with adjacent sides VW. So VW define a parallelogram, and so this V cross W gives the area of that parallelogram. Last, we looked at the equation of a plane, normal to the vector n is equal to ABC and containing the point x naught, y naught, z naught. And we have this equation, which we had looked at when we looked at the dot product, but it was important to understand the basics because we extended this in several examples, the last one being quite involved. So it's important to know how this equation came out and the thinking behind it, and we did several examples of this. As a review, I have three questions here, so you can pause the video, work the problems, and on the next slide, I will have the solutions. So these are my solutions, and just a quick comment, since this kind of comes from this parameterized line equation, comes from the first section of chapter 1, which is about vectors in Rn. This is a parameterization of a line, where this is a point on the line, and this is a line segment, or a vector, that's on the line. And since it's perpendicular to this vector, when I dotted it, it should be equal to 0. And that's it for this video. Thank you for watching.